Hello. What I want to do is continue with our discussion of use substitution and essentially common procedures for fitting the integrand to basic integration rules. And the thing that you want to have available as you do this is make sure you have your table of 20 basic indefinite integrals that we passed out in class today. It's also This table is also available on Canvas when you go to module and click on week 1. Okay. So in class today, we were able to do several examples for use substitution. And we did an example where we expanded and simplified the integrand. We did an example where we separated numerators. Now we're going to do an example where we simplify an improper rational function. And this is the technique that we use in order to fit our integrand into something where we can apply the basic integration rules. Okay, so let's go ahead and get started. This is the example that I want to show you. Suppose we need to integrate this right here. So what you'll see is you'll see this little zoom box here. I'll write down on the bottom, right? So like here I am, I write down here and it shows up top, but watch my pen down here at the bottom, okay? So I'm going to erase so that I can actually get started here. Now for this integral, we're trying to integrate x squared divided by x squared plus 1. And what is the topic? The topic is to simplify improper...
2030.
Thank you. Simplify improper rational functions. So just remember that a rational function is a function of the form p of x over q of x, where p and q are polynomials. P and q are polynomials. So, polynomials. So this integrand is definitely a rational function because the numerator is a polynomial and the denominator is a polynomial, right? They're both quadratic. And it's improper. We have an improper rational function because the degree of the numerator is, so this is the degree of the numerator is greater than or equal to the degree of the denominator. Right? So in that case, we have an improper rational function. So just to review, because this is actually going to come up in a few days when we study partial fraction decomposition, what is the degree of the numerator? The degree of the numerator is going to be 2, right? Because x squared is going to have a numerator of 2. The degree is the highest power of that polynomial. Okay, and what is the degree of the denominator? The denominator is going to be of degree 2 as well. So, since the degree of the numerator is greater than or equal to the degree of the denominator, we have that our rational function is improper. So the purpose of this technique is to say that, hey, look, you can save yourself a lot of time and you can solve this simply by rewriting, simplifying this improper rational function. Okay. Now, we've got one technique, which would be one technique would be to use long division or synthetic division of polynomials. Now this, I think you talk about it in pre-calculus, synthetic division of polynomials. Okay, and just to remind you what that would look like, it's very similar to long division in general. Okay, so you would say, just like you would say, what is 17 over 3? And you would say, oh, okay, well, let me rewrite that as how many times does 3 go into 17? You'd say it goes in there 4 times. Oh, wait, it goes in there 5 times, right? And then 15. So I've got left over. It's got 2 left over. So we say 5 with the remainder of 2, right? And so then we would go back here and rewrite 17/3 as 5 and 2/3. That same process is what we would do for long division. So we would take our denominator, which is x squared plus 1, and divide x squared, divide our numerator by the denominator. And then we would say, how many times does x squared plus 1 go into x squared? It goes in 1 time, right? So you've got x squared plus 1. Subtract, you get -1. How many times does x squared plus 1 go into -1? 0 times, so we've got a remainder of -1. And we would write that, therefore, x squared over x squared plus 1 is equal to 1 plus -1 over x squared plus 1. Okay? Which we could also write this as just 1 minus 1 over x squared plus 1. Now, we can do that, and that's totally fine. Right? So that's totally fine. We're essentially, let me clean this up a little bit. We're essentially using long division to rewrite our integrand of x squared divided by x squared plus 1 as 1 minus 1 over x squared plus 1. But there's a shortcut, a shorter way. Shortcut. And so here's the shortcut. The shortcut is to say x squared over x squared plus 1. So in your mind, you're thinking, if I had plus 1, then I've got 1, right? Because I have x squared plus 1 in the numerator and in the denominator. But I can't just add plus 1. Also, we need to subtract plus 1 so that my expression remains the same. Now, I'm back to that second technique that we talked about, which is to, what was the second technique? The second technique was to separate the numerators. Remember we did that? So that's essentially what we're doing here. So we would look at this and we would say, okay, I've got x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. 1 minus 1 over x squared plus 1. And we get exactly the same as we did using long division. Okay, so this is part of numeracy. Numeracy, this is very sophisticated numeracy. When you see this expression, x squared over x squared plus 1, in your mind, you're thinking, oh, that's really close to x squared plus 1 over x squared plus 1. Oh, and now I need to correct, right? I have a correction factor. And then all of this kind of happens in your head. Okay? All right, so let's actually integrate. So I'm going to erase this. The integrating part is easy. What's difficult is recognizing that you need to rewrite or simplify the improper rational function. So here we go. So once I write this, so I'm going to rewrite it. I'm going to say the integral of x squared over x squared plus 1 dx is the same as the integral of 1 minus 1 over x squared plus 1 dx. Okay? And now I've got the integral of 1 dx minus the integral of 1 over x squared plus 1 dx. Now what is the integral of 1 dx? Oh, that's just x. And what is the integral of 1 over x squared plus 1? Remember, this is the tricky one. We have to kind of remember it's on our sheet, arctan or inverse tan of x. And then I add my plus c, and I'm done. Something actually that I want to emphasize is don't forget that you can always check your integral by taking the derivative of your answer. So check your integral by finding the derivative of your answer And the derivative of your answer should be the same as the integrand of your integral. Okay. All right. There we go. Thank you.